All right, so today we are gonna look a little bit at our limits and what limits do. So take a second and see if you can answer these first few questions. So Steve Nash has the second highest lifetime free throw percent at 90.43%. So you decide to study his free throw in greater detail to improve your own shot, but unfortunately the video freezes. How accurately can you guess the height of the ball after 5 milliseconds? So what information would you want to know to make your prediction? So right here, we're going to have a video that's freezing, yes. So what would you want to know? So if we knew what the height was before, so the height before and after. So if I knew both of those two things, I could kind of figure this out. So the data below kind of models the ball's path. So the time is given in milliseconds and the height is given in feet. So the data tracks the height before and after the video freezes. So time in 0 milliseconds, the height's going to be 7. 4.5 milliseconds is 14.5. So as it approaches that 5 milliseconds, what is happening to, it's getting close, it's 14.992. And then when I go this way, when I'm looking this way, what is it getting close to? So before the video freezes, use the data to make an estimate of the ball's height at 5 milliseconds. So what do you think? 5 feet? And after the video freezes, what do you think? It's also going to be what? I think I said 5. I meant 15. I'm sorry. 15 feet. So what does that mean? So these two things are equal to each other. Yes. So to make this work, it's a continuous function, right? So it's continuous. The ball's got to go up and then go down, right? So the ball must have been at 15 feet. So this is your limit notation. Okay. All right. So before the video freezes, so as I'm approaching 15 as I'm approaching 5 from the left-hand side. So we can say the limit as my time approaches 5 from the left of that height function, what is that limit going to be equal to? And it's going to be equal to 15. All right, so after the video freezes, so this is now coming from 5 milliseconds from the right side. So my notation changes just a teeny bit. So it'll be the limit as your time approaches 5 from the right side of that height function. So it's also going to be equal to 15 feet. So since these two things are congruent, we can say, so we can say then the limit as time approaches 5 of that height function is going to be 15. Okay. All right, so now looking at a graph, so now you know the height of the ball in feet was given by this function here. So trace the graph as t increases towards 5. What y value is being approached? So as I'm going this way, so as I'm increasing, so I'm increasing, right? So as I increase, what am I approaching? So I'm approaching 15 feet. And then what happens as I decrease? So if I'm going this way here, I'm going kind of all the way over here. So it's also 15 feet. So without the graph, how easy could we have found the height of the ball as t gets closer and closer to 5? Okay. So we could plug in numbers close to 5 and plug in 5. So this is our direct substitution method. So that's our first kind of strategy of finding a limit. Okay. Alrighty, so this is important. So a limit is an intended y value. Okay, we've talked about limit notation, but just so you can remember, so the limit as x approaches some value, and then this is my function, right? So we say limit as x approaches a. That's what that means. Okay. All right, so let me go draw a little graph here so we can kind of see what's going on. I'm going to put A right here. I'm going to put B right here. C will be here. Okay. We're going to have a little open circle at B. So we're going to have something like this. We're going to have a little asymptote at C. Just going to go this way. Just, I don't know, something crazy. Okay. So right here, the limit from the left of A, so the limit as x approaches A from the left of that function is going to be equal to the limit as x approaches A from the right. They're the same. So that means that the limit as x approaches A is going to be that L value. So let's put an L right there. Most of the time our L is going to be a finite number, so something that we can count. But we also have infinite limits as well. But most of the time it'll just be a finite number. Okay, so I also have drawn things where limits don't exist. So I'm going to give you okay, so a limit doesn't exist at B, and that's because the limit as x approaches B from the left does not equal the limit as x approaches B from the right. So those two things do not equal each other. So does not, we say DNE a lot of times, does not exist. Okay. We also say that the limit does not exist at C either, because what is happening here? The limit as x approaches C from the left of that function, so since it's going from the left, it's going to positive infinity. And then the limit as x approaches C from the right is going in the opposite direction. It's going to negative infinity. So since those two things don't equal each other, then that limit does not exist. So the limit as x approaches C does not exist. The individual limits do exist because they are going to positive or negative infinity, but they don't exist together. Okay. All right, so take a second, and see if you can answer these questions here. Pause the video and then I'll put the solutions up. All right, so let's see how you did. So this one, the limit as x approaches 3 from the left-hand side. So where is 3? So right here, right? So as it approaches 3 from the left-hand side, it's going to be approaching 0. As I approach 3 from the right-hand side, it's also approaching 0. So since those two things equal each other, it does not exist. I mean, it's going to 0. Sorry. So, and then the function evaluated at 3 is also 0. All right. All right, so what about this one? So the limit as x approaches 1, so 1 from the negative direction, so it's going down here to -1. And the limit as x approaches 1 from the positive direction is going to 4. Those two things don't equal each other, so it does not exist. But the function is equal, evaluated at 1, it is going to be equal to 4. Okay. All right, so this could look like anything, so it doesn't have to look like what I drew, but the limit as x approaches 2 from the positive direction, well, and I didn't even do that right. Miss A, what are you doing? Crazy lady. In my head, I was thinking the negative side came first. All right, so from the negative direction, it's 3. So like this, I don't know. It could look like anything, like I said. And then from the positive direction, it's going to 0. So something like this. So this is what this will look like. So there's a gap in the graph. All right. What about for number 3? So it says evaluate the limit. If you plug in a 0, you will get an error message. So I wanted to kind of show you something. So what's happening to this graph? So as I approach from the left side and from the right side, what is it going to approach? And it is going to approach a 1. So once you plug those in, see you're getting smaller and smaller and smaller. So, and they're both approaching 1 from both sides. So the left of 0, so as when it approaches from the left side and when it approaches from the right side, they're both going to be equal to 1. Okay. All right. Let me know if you have any questions.